everyone, welcome back to my channel. I'm Miss Merkin if you are new here. If you're not, welcome back. Today we're going to be talking about a process called local linearization, which is basically just a calculus process that we can use to approximate the outputs of functions at particular values for x. Now we use this process on functions where it's a little bit more difficult to just put in an input and algebraically get an output. So we can use this strategy that basically uses equations of tangent lines to approximate outputs. Okay, so I'm going to be doing this video a little bit different than some of my other videos. I'm going to do a lecture-based guided notes style. So the guided notes that I'm using, I'm going to be screen sharing somewhere over in this area, and you can follow along with me. Okay, so let's go ahead and get started. Okay, so we are actually going to start here with a warm-up problem. So now would actually be a really great time to pause the video, read through the warm-up problem, and try for yourself. And then, once you've done that, you can unpause and I'll go through it. Okay, so hopefully you paused. Let's go ahead and go through the warm-up. So the warm-up says, let point x sub 1, y sub 1 be a point on the graph of the equation x squared plus xy plus y cubed is equal to 8. Part A says, if x sub 1 is equal to 0, find y sub 1. So it's basically, if your input is 0, what would the output of this function be? And give your answer in coordinate form. Okay, so let's go ahead and go through this. Now, we have our function, which is x squared plus xy plus y cubed is equal to 8. So really, all I need to do is anywhere I see an x, I'm going to sub in a 0. So I have 0 squared plus 0 times y plus y cubed is equal to 8. Well, 0 squared is just 0. 0 times y is 0, and then we're just left with on our left-hand side, y cubed is equal to 8. So to get y by itself, we'll take the cube root of both sides, and we are left with y is equal to 2. Okay, so our coordinate, if x sub 1 is 0, y sub 1 is going to be 2, so in coordinate form it would be the point 0, 2. Pretty straightforward for that one. That was an example where I put in the input, and my output is relatively simple to get. Alright, part B says if x sub 1 is equal to 0.1, and we're going to find y sub 1. So you can use a calculator for this one. We're going to give our answer in coordinate form once again. So this looks like 0.1 squared when we sub in 0.1 for x plus 0.1 times y plus y cubed is going to equal 8. Okay, so now I have 0.1 squared, which will be 0.01, plus 0.1 y plus y cubed is equal to 8. Now, I'm already noticing that it's going to be a little bit more difficult to find y. However, we do get to use our calculator, and I will put a little insert in once I do one more step to show you how to do this on your calculator. There are several ways. I'll show you one method. Okay, so I'm going to subtract 8 from both sides and kind of reorder my function. So we're going to go ahead and reorder it to be y cubed plus 0.1y. Now we're going to subtract 8 from this. So 0.01 minus 8 is going to give us a negative 7.99. And that's going to be equal to 0. How to solve the equation y cubed plus 0.1y minus 7.99 equals 0 using a graphing calculator. This is the TI-84 plus C Silver Edition. Okay, so first you're going to hit y equals. We're going to just change it to a function of x just for the sake of solving quickly. So we're going to go ahead and put alpha x, and it's cubed, plus 0.1, we're going to say alpha x, minus 7.99. And we're going to hit graph. It doesn't matter that this is a little bit of a bad window, but the whole goal here is really to find out where this function hits the x-axis. Where is this function 0? So to do that, you can hit the second button, and then where it says calc above the trace button. You can hit intersect, or actually let's go ahead and do 0 because we're not doing intersect. Go ahead and hit 0 and hit enter. And then we are going to give it a left bound, so I'll click about here, and a right bound, so I'll go ahead and click about here, and then it wants you to guess where that intersection point is, and it will find the 0 for you. So it's about 1.982 where our function is equal to 0. So once we did it on our calculator, we got y was approximately 1.982. I always have my students round to 3 decimal places at least, just because that's what College Board prefers for AP. Okay, so our coordinate point would look like 0.1, comma, 1.982. Now this is an approximation, it's not exact because we had to use our calculators, but it's probably pretty close, at least 3 decimal places accurate. So, okay, so at the bottom I put a little note that basically says, notice Part A was a lot easier than Part B, and we had to actually go and use a tool to get some help in order to get the answer for Part B. So, what that means is we actually have a smarter way to get these approximate values where we won't actually need to go to our calculators to get an answer. And that's going to be the process of local linearization. I mentioned before, we're essentially taking a line that's tangent to the original function at some point and using the equation of the tangent line to get the approximate coordinate of a nearby point. Okay, so I gave you a little bit of an intro. We're going to move on to the actual notes piece. So this part says, sometimes finding the value of a function is very difficult or even impossible. We can use the process of local linearization to approximate, goes in that little bubble if you're following along with my guided notes, the output of a function at some x value. So here are the steps for local linearization. Step 1, we want to find a coordinate point on the function that has an input or x value, we'll say x value. Near the x value you are trying to find an output for. So for example, in our example problem, we had 0 for our first x value and 0.1 for our second. Very close, right? So the output at 0.1 shouldn't be too drastically different from the output at 0. So that way we can actually use that point or a tangent line at that point to come up with an approximation for the other point. The next step is to take the derivative of the function with respect to x. You want to make sure you solve for dy dx because you actually want the slope of this tangent line. It makes it a lot easier to then calculate the slope. You want to then plug the coordinate you do know into dy dx to find the slope of the tangent line. You then want to write the equation of the tangent line using your slope from step 3 and the coordinate you used in step 3, and you might as well just keep it in in point slope form. You can always rewrite it into y equals mx plus b form. It's completely up to you. Then we want to plug the x coordinate of the output you are trying to approximate into your equation from step 4, and we want to solve for y, basically our output, or approximated output for our original function. Okay, so I think this is a lot easier for me to explain if I actually go through an example. So we're going to do the first example together. You are, of course, always welcome to pause and try the first example on your own, but I will go ahead and go through the first example now. Okay, so we're going to go ahead and work through the first example, which says the point 0, 2 is on the equation x squared plus xy plus y cubed is equal to 8. We're going to use local linearization to approximate the y-coordinate when x is 0.1. This should all seem very familiar. Then it says, how does it compare to your answer in the warm-up problem? So we're taking the point 0, 2 from the warm-up and the same equation, and we are going to now just use local linearization to approximate the y value when x is 0.1, as opposed to plugging and chugging and solving for it like we did in part B of the warm-up. Okay, so let's go ahead and go through the process. First, we need to take our equation, which is x squared plus xy plus y cubed is equal to 8. And what we are going to do is take the derivative of both sides with respect to x. The reason we're doing that is because we want to find dy dx, which is the slope of the tangent line. Okay, so we need to use a little implicit differentiation here. The derivative of x squared with respect to x is 2x, plus we have to use our product rule here. Derivative of x with respect to x is 1, so we're just left with y plus x times the derivative of y with respect to x is just dy dx, plus the derivative of y cubed with respect to x is 3y squared times dy dx. Don't forget that chain rule, like hook-on factor we like to say, is equal to the derivative of 8 with respect to x is 0. Okay, so I have 2x plus y plus x times dy dx plus 3y squared times dy dx is equal to 0. Now what we need to do is subtract 2x and y, subtract y from both sides. And we are going to simultaneously, in the next step, factor out that dy dx because we want to solve it for it. So I'm going to factor out dy dx from the two terms that are left in the left-hand side of my equation. So times x plus 3y squared is equal to negative 2x minus y. Okay, and then my final step is just to divide both sides by x plus 3y squared. And I have now solved for dy dx, which is equal to negative 2x minus y over x plus 3y squared. However, for my tangent line, I'm going to be using the equation of the line tangent to the point 0, 2 to help me approximate the y-coordinate when x is 0.1. So what we're going to do here is plug in the point 0, 2 to get the slope of that tangent line. So I'm going to kind of do this up here. I'm kind of running out of room a little bit. So we have dy dx of, and we're going to plug in the point 0, 2. So that would be negative 2 times 0 minus 2 all over 0 plus 3 times 2 squared. Okay, let's go ahead and simplify this. So negative 2 times 0 is 0, minus 2 is negative 2, all over 0 plus 2 3 times 2 squared. 2 squared is 4 times 3 is 12. Negative 1 over 12 simplifies to negative 1/6. Let me move this a little bit so I can draw. It gets a little squiggly towards the edge there. Okay, so now we can use that for our equation. So the equation of the tangent line in point slope form is going to be y minus our y coordinate, which is 2, which equals our slope, which is negative 1/6, times x minus our x coordinate, which is 0. So when we simplify this out, we can actually easily put this one in y equals mx plus b form. We get y equals negative 1/6 x plus 2. Okay, from here, I know it seems like a very long-winded process, we can now plug in 0.1 for x into the equation of our tangent line. So we have y of 0.1 is equal to negative 1/6. Hope you guys are okay with me rewriting 0.1 as 1/10 just to make it our math a little easier here, plus 2. Okay, and let's see, we have y of 0.1 is equal to, we have negative 1/6 times 1/10 plus 2. And so when we do that, negative 1/6 times 1/10 is negative 1 over 60. We could rewrite 2 as 120 over 60, so it would be 119 over 60. Now, just to make it a comparable answer, we could punch this in our calculator and get a decimal. Let me go ahead and do that really quickly. So once you do that, you approximate and get about 1.983, which is 1/1000th off from what we got in part B when we approximated using our graphing calculator. So very close using the equation of the tangent line here. Now the longest part of this process is finding the equation of the tangent line. Once you've done that, then it's pretty straightforward and we can basically approximate using that same tangent line equation to get any other points that are around the point 0, 2 as well and get a fairly accurate approximation. Okay, so basically what this is saying is when x is 0.1, we can approximate that the output is about 1.983. So that's how we interpret that. Okay, so here's where I encourage you to once again pause the video, go ahead and do problems 2 and 3 on your own, and then you can unpause and I will go over them for you. Okay, so hopefully you paused. Number 2, we're going to start by going over this one. It says, if 1, 4 is a point on x squared plus y squared plus 3x is equal to 20, use the equation of a tangent line passing through the point 1, 4 to A. Approximate the y coordinate when x is equal to 1.01. Part B, we're going to approximate the y coordinate when x is 0.99. Now, the point we're given is 1, 4. The x coordinate is 1, which is really close to both x coordinates, so we could use the same equation of the tangent line for both parts A and B. So let's go ahead and start part A. So we have to use the same process where we take our equation x squared plus y squared plus 3x is equal to 20. And we're going to take the derivative with respect to x of both sides. Okay, so the derivative of x squared with respect to x is 2x, plus the derivative of y squared with respect to x is 2y times dy dx. And then the derivative of 3x with respect to x is just 3. Is equal to the derivative of 20 with respect to x is 0. So I'm going to subtract 3 and subtract 2x from both sides. So I end up with, So I end up with 2y times dy dx is equal to negative, sorry, that looks like a 1, 2x minus 3. And then we're going to divide both sides by 2y. We end up with dy dx is equal to negative 2x minus 3 all over 2y. Okay, so now we need to find the equation, or the actual slope of our tangent line. So we're going to plug in the point 1, 4 to our dy dx equation. Okay, so dy dx of 1, 4 is equal to negative 2 times 1 minus 3 all over 2 times 4. Okay, so the equation, or the slope of our tangent line is going to be negative 2 minus 3, which is negative 5, over 2 times 4, which is 8. So our slope is negative 5/8. Okay, so now we need to write out our equation. So we have y minus our y coordinate, which is 4, is equal to negative 5/8 times x minus our x coordinate, which is 1. Okay, I'm just going to go ahead and add 4 to both sides just to get it in y equals form. It's not in y equals mx plus b form, but that's okay. So we have y equals negative 5/8 times x minus 1 plus. Okay, so now we will plug in, let's see, 1.01 for x. So we have y of 1.01 equals negative 5 over 8 times 1.01 minus 1 plus 4. Okay, so we could manipulate this and spend some time adding these numbers up and all that kind of stuff, but let's go ahead and just use a calculator to approximate this. Okay, so after punching that into a calculator, we get y of 1.01 is approximately 3.994. So that means the y-coordinate when x is 1.01 is approximately 3.994 according to the local linearization process that we used. Okay, so then the next one says approximate the y-coordinate when x is equal to 0.99. So close to 1, so we can use the same exact equation. So we have y is equal to negative 5 over 8 times x minus 1 plus 4. We're going to sub in 0.99 for x. We get negative 5 over 8 times 0.99 minus 1 plus 4. And we're going to go ahead and punch that into a calculator as well. Later we get y of 0.99 is approximately 4.006. I'm doing 3 decimal places again. Okay, so we did number 2. Let's go ahead and move on to number 3, which says if f of negative 1 is equal to 5 and f prime of negative 1 is equal to negative 3, we're going to use local linearization to approximate f of negative 0.9. Okay, so once again, feel free to pause here, do it on your own, unpause, and then go over your answer with me. Okay, so we are given f of negative 1 is equal to 5. Well, that's the point, negative 1, 5, that we're going to use for our equation of our tangent line. We're also given that f prime of negative 1 is equal to negative 3. So what that means is my derivative at negative 1 is negative 3. Another name for that is the slope of my tangent line. So the slope of my tangent line is negative 3. So from there, I can come up with my equation, which would be y minus my x coordinate, which is, my y coordinate, which is 5, is equal to the slope of my tangent line, which is negative 3, times x minus my x coordinate. So the equation of my tangent line is y minus 5 is equal to negative 3 times x plus 1. And of course, you're free to put this in y equals mx plus b form. So if we did that, we'd get y equals negative 3x. And it would be negative 3 times 1, which is negative 3. And then we'd add 5 to both sides, so it would be negative 3x plus 2. Okay, so we are going to use it to approximate f of negative negative 0.9. We're going to just take our equation of our tangent line and sub in negative 0.9. When we do that, we get negative 3 times 0.9 plus 2. So y of negative 0.9 is actually equal to 4.7. Okay, and so what that means is f of negative 0.9 is approximately 4.7. And that would be our final answer. Okay, so this was my lesson on local linearization. I hope you enjoyed, and thank you for watching.